I record to the cloud. Okay, it's my big pleasure to introduce Fabrizio Catanese from University of Bayreuth. And Fabrizio will talk about nodal surfaces, coding theory, and cubic discriminants.
Okay. Giovanni, thank you for the invitation to give this talk. When I accepted, I was hoping that this big article in several parts would be already written, but still it's growing. And what I want to talk is about some subject which has some history. So coding theory for nodal surfaces was introduced in the late 70s by Beauville, and parallel to some work of mine on even sets of nodes. Then there were some results in the 90s, and after that the subject has been dormant, and I would like to push so that the research goes further. So this is the outline. I will give an introduction explaining the situation. Then I will talk about binary codes. Then I will talk, I will talk about quartic surfaces, quintic surfaces, sextic surfaces, and in the end, cubic discriminants. Oh, why? No, this is, I don't know why it went to the end. Okay, let me go like this. Okay, so I will consider during the talk nodal hypersurfaces. So hypersurfaces of degree d in of dimension n, and defined by a homogeneous polynomial of degree d, which I will call capital F. And we assume that the hypersurface is isolated singularities, so it has finite number of singular points. And the singular point is a node if the quadratic part of the Taylor development of F at the point is of maximal rank, which is n, the dimension of the space. And so nodal hypersurface means that its singular points are just nodes. And somehow the new point of view is to use this, the coding theory, to study nodal Severi varieties. So I propose the name of nodal Severi variety is the family, the locally closed set in the projective space parametrizing all hypersurfaces of degree d, consisting of the nodal hypersurfaces of dimension n, degree d, having exactly ni nodes as singularities. So I think the notation should be clear. Ni stands for nodes, d for degree, and n is the dimension. The reason to call it nodal Severi variety is that Severi studied the case of plane curves n equal 1, where one has to add the hypothesis that x is irreducible. And it turns out that this F1D nu, this Severi variety, is smooth and connected. Of course, Ni has an obvious upper bound for curve, d minus 1, d minus 2 over 2. And this was important because Severi made this assertion in the unhung appendix F to this Vorlesungen, had an incomplete proof, and this proof was rescued some 60 years later. And up to now, the name of Severi varieties has been more used for the case of nodal curves lying on other algebraic surfaces. Just to give a flavor of what we expect, just take the linear subspace in the space of conics, the space of diagonal conics. So the parameter space is this projective plane with the coordinates A0, A1, A2. And of course, being singular means that exactly one of these coefficients vanishes. So the parameter space is this triangle minus these 3 points. So there are three connected components of this variety. And in general, we get a stratification of this projective space in a certain number of strata. So what I want to show is that there is a similar picture, even if more complicated, in higher dimension. So what are the basic questions for nodal Severi varieties? Well, when is this variety non-empty? In particular, if we define mu n of d, the maximal number of nodes that can have a hypersurface of degree d of dimension n, can we determine this maximum? Another question is, when do we have a no gaps phenomenon? So that once we determine this maximum, then Fn d ni is non-empty for all ni smaller or equal to the maximum. When it is connected irreducible, how to determine its components, when is it smooth? Of course, these questions are very difficult. Already the case of surfaces to which I will devote myself, n equal 2, the state of the art is just that the maximum is known only for d at most 6. And of course, the maximum is for a plane 0, 1, 4, 16, 31, 65. Okay, d equal 1 or 2, we have a plane, has no singularities, then the quadricone has 1. For d equal 3, there is the so-called Cayley cubic, which has 4 nodes, and it was first apparently found by Schlefly and studied by Cremona and Cayley. And for d equal 4, we have the Courmet surfaces. The first example was found by Fresnel in 1822, and they have 16 nodes. And in 1940, there were the d equal 5, there are Togliatti quintics. Togliatti gave a construction in order to show that there are quintics with at least 31 nodes. And Beauville in 79 showed that 31 is the maximum. And a similar situation is for sextic. Barth gave an example in the 90s of a surface with 65 nodes. And then Jeffy and Ruberman showed that 65 is the maximum. And the proof was then simplified by Jonathan Wall, Pignatelli, and Tononi. And in this range, the answer is that there are no gaps. So for all surface of degree up to 6, and for each ni number of nodes which is not greater than the maximum, there exists one surface with the number nu of nodes. And for degree 6, this was proven by my work with Ceresa in 79. For n equal 4, it was proven by Ron in 1886. And the only new result is here for the case d equal 5. So we have no gap for nodal surfaces if the degree is up to 6. And so here you can read, this means that for each ni not greater than mu of d, there exists a nodal surface of degree d with precisely new nodes. Of course, the answer to this question is classical for degree up to 3. The nodal Severi varieties are smooth and irreducible. Now we go to the case d equal 4. And in spite of a lot of classical work as books, the case of nodal Severi varieties of quartics was until now open. And I want to give now the first theorem, which classifies the irreducible components of the Severi, nodal Severi variety of quartics with ni node, where ni is at most 6. This is the result. If Y is a nodal quartic surface is in P3 with ni nodes, and of course, ni is at most 16, I denote Y star, the smooth part of Y. Then the theorem says that the fundamental group of the smooth part is finite and equal to Z mod 2 to the K for ni at most 15. and it is isomorphic to a binary code, which I will introduce later, which is in turn determined by its dimension. If you get nu equals 16, as it is well known, the fundamental group of the smooth part is the semi-direct product of z to the fourth times z mod 2 acting on z mod 4 by -1. And here the codes are the so-called Kummer codes. There are two codes, and K Kummer and K prime Kummer. And the subset of the nodal Severi variety F for nu corresponding to nodal quintics with new nodes and the fixed binary code K prime is smooth and connected, in particular irreducible. And the key point is that the possible codes of K prime appearing are in particular all the shortenings of the extended Kummer code K prime Kummer. So this is the theorem. It classifies all the components of this Severi variety through these codes, which are the shortenings. So to illustrate the result better, so if you fix the binary code K prime, we get a subset which is smooth and connected. We get all the shortenings of the extended Kummer code. And so it follows that the nodal Severi variety F4 Ni has exactly one irreducible component if the number of nodes is between 0 and 5 and between 14 and 16. Two components if nu is 6, 7, 13. Three irreducible components for Ni equal 8, 9. 4 components for Ni equal 11, 12, and exactly 5 irreducible components for Ni equal 10. So we have a stratification made of 34 strata, where each stratum is in the boundary of another if and only if the corresponding extended code admits the other as a shortening. Of course, let me now, I've been speaking about shortening and so on and codes. So to explain the statement of the theorem, I need some basic notions of coding theory. So I go to binary codes. So if F is a field, an F linear code is just a vector subspace K of dimension small k of the vector space F to the S of functions on a given set S with values in the field F. And two such codes, K1, K2, are equivalent if there is a bijection of the two sets carrying the first code to the other. And I will concentrate mainly on the case of a binary code, which means that F is the field with two elements. Now, given a code, so this is a key notion, very simple. If I have a subset N of S, the shortening with respect to N of the code K is just the intersection of K with the subspace of functions in K with support in N. The projection of a code determined by a subset N is just the image of K via the restriction map. You take the functions on S and you take the restriction to N. Therefore, the shortening with respect to N is just the kernel of the projection determined by the complementary sets. Of course, you can take a code and add as many zeros as possible, but this doesn't really make the code more complicated. So the effective length N is the cardinality of the union S prime of the supports of all the functions in K. If you take a vector in K, the weight, also called Hamming weight, is the cardinality of the support of the function, V. And the minimum weight of the code is the minimum of the weights of non-zero vectors in K. Now, the dual code is important. Dual to the injection of K in F to the S, we have a surjection of F to the S to K dual. Now, the dual code is just the kernel. So it's the perpendicular K perp to K in Fs. And given a subset of S, duality exchanges the projection with the shortening. So if you take the perpendicular to the projection, this is the shortening of the perpendicular. Now, the simplest code is I call it the biduality code, because you just take K, and K can be thought as, by bidualities, these are linear functions on the dual space. And so, since a linear function always takes 0 on the origin, I get a mapping of K to F to the functions on K dual minus 0. In this case, each non-zero vector has weight exactly 2 to the K minus 1, where K is the dimension of K. And its dual code of this biduality code is called the Hamming code, because Hamming really found the code in a more complicated way. But the biduality code is also called the Simplex code, and code theorists call it the dual Hamming code. But for us, it's simpler to say that there is a biduality code or Simplex code, and then we go to the dual code, which is the Hamming code. And an important concept introduced by McWilliams is the weight enumerator function of K. You take a generating function, some ai x to the n minus I y to the I, where n is the effective length, and ai is the number of vectors of K with weight equal to I. And the McWilliams identity determines the weight enumerator of the dual code. The weight of the dual code is 1 over 2 to the K, wk x plus y x minus y. So I think it was Jonathan Wall who showed that the McWilliams identity makes some proofs much easier. So let me explain the use of the McWilliams identity in the simplest case. The McWilliams identity reads out as a series of identities, and the first two are the sum of the ai is 2 to the K minus 1, and the sum of the number of elements of weight I multiplied by I is the power of 2 with exponent K minus 1 times n, the effective length. Assume now that we have a code K where all the weights are just 2 to the m. And, okay, K will be the dimension of the code, n is effective length. Then the second identity combined with the first says that here I is equal to 2 to the m, g to the m times the sum of the ai, which is 2 to the power K subtracted 1. This is equal to 2 to the power K minus 1 times n. So it follows that as a rational number, n is an odd number times the power of 2. And since n is an integer, the exponent must be non-negative. It follows that K is at most n plus 1. And it is not so difficult to prove directly that if K is equal to n plus 1, we have the simplest code. And in general, if the weight is 2 to the m, we have a subcode of the simplest code. In general, Bonisoli showed that each code with only one weight is obtained from the simplex code simply via a product structure on the set S, we write S equal S1 and S2. We take the simplex code on S2, and then we take the functions of X and Y, which are just depend on Y. So it's just a repetition, a code where with only one weight is a repetition somehow of the simplex code. Now, for our purpose, I need a new type of codes. A bicolored F-linear code is a vector subspace K prime of the vector space of functions on the disjoint union of two sets. Again, equivalence if there are bijections of the first sets A1 with A2, B1 with B2, carrying K prime 1 to K prime 2. In practice, in our situation, B consists of a single element H, and where H stands for the hyperplane section. And moreover, quite often, K prime is determined by its projection inside F to the A. Okay, so we just saw that linear functions yield the biduality simplex code. And next, there are the polynomials of degree at most 2, which yield the Reed-Muller codes, and of which the Kummer codes are a special case. I take an affine space of dimension m over the field with 2 elements, so A is F2 to the m. Then the first Reed-Muller code is the space of affine functions from this affine space to F2. And the second Reed-Muller code is the space generated by K and a non-degenerate quadratic form. These codes have respective dimensions, K equal m plus 1, m plus 2, and the Kummer code, extended Kummer code, are the ones obtained for m equal 4. And it is easy bilinear algebra. This is, let me explain it, because this is not, we don't do bilinear algebra over a field with 2 elements, but every quadratic form can be written, so we can reduce to the case where Q of X is X1, Y1 plus X2, Y2 plus XH, YH, because each polynomial function of degree 2 over F2 has one of these affine normal forms, a sum of products plus a square, a sum of products, or a sum of products plus 1. But since we already have the constants and xk plus 1, this is a linear form, then we can reduce to this form. And the people, I mean, if m is equal to 2k, so this is of full rank, these two cases, 1 and 2, they differ because these are just related to the odd even theta characteristics. In case 1, the number of zeros is 2 to the k minus 1 multiplied by 1 plus 2 to the k. And in the odd case is 2 to the k minus 1 multiplied minus 1 plus 2 to the k. So theta characteristics depend on this easy bilinear algebra over C mod 2. Now, the next question is, there are several ways to describe the binary codes as attached to a nodal surface. And there are 2 binary codes, okay? So a first way is you take a nodal surface, and now you take K in Z2 to the nu is the image of the dual map to the first homology surjection. So I take the homology of the smooth part, and here the direct sum of Z mod 2, I just take some punctured neighborhoods of the nodes, and this has homology Z mod 2. So I take the homology of this union of punctured bolts around the nodes, I map it to Y star, and I get this surjection here. And dualizing, I get the code. Another way to get the the extended code is to blow up y tilde at the nodes and let H be a smooth hyperplane section. Then the extended binary code is contained in Z2 to the Ni plus Z2H, H is the hyperplane class, is the kernel of the map, the direct sum of Z mod 2 times EI plus Z mod 2H in the homology of y tilde Z mod 2. And this was the definition more or less used by Beauville, except that he was not considering the extended code. So we have this second definition. And what is important is that K prime, okay, if it determines something, I take the second cohomology of y tilde with coefficients in Z. I call it lambda because it's a lattice. Okay, this is a free lattice. Okay, inside I have the lattice generated by the curves EI and H, but this lattice is not saturated. If I take lambda intersected the rational multiples of L, I obtain something more, the saturation. And the answer is quite easy. The saturation of L is the set of elements 1/2 sum of AI, EI plus BH, such that sum of AI, EI plus BH modulo 2 is in K prime. So what is important is that this extended code determines a primitive sublattice of the second homology. Sorry, this is... Okay, so I repeat here what I said. Lambda is the second homology. L is the sublattice freely generated by EIH. And the saturation is determined by K prime. Now, this is important because in the 70s, Nikulin developed a theory of primitive embeddings of lattices, generalizing results of Milnor and other to the non-unimodular case. The results of Nikulin offer criteria, not always easy to apply, for existence and unicity of such embeddings. These results, of course, are very useful for K3 surfaces, of which resolutions of nodal quartic surfaces are a special case. So we take a nodal quartic surface Y, its resolution Y tilde is a K3 surface, we fix lambda, and if we fix extended code K prime, then by the results of Nikulin, there exists a unique primitive embedding of this saturation of L inside lambda. So this is a fact, which I prove, and then this allows to prove, to use the Torelli theorem for K3 surfaces, and this shows that the nodal quartic surfaces with code K prime are parametrized by at most 2 smooth connected components, exchanged by complex conjugation. But I claim that there exists only one connected component. So all I have to do is to exhibit such a quartic with a code K prime and with a given number of nodes, which is real. And this can be done in a very concrete way. I call this Kummer quartic the Duke of Cefalù. So Kummer surfaces are quartic surfaces with 16 nodes obtained as A divided by plus minus 1, where A is a principally polarized abelian surface. But the most simple such example, important for many reasons, is just this simple equation. I take the sum of the squares of xi squared minus 3 times the sum of the fourth powers. This is nice because, first of all, is defined over z. Actually, you can even see that you can divide the equation by 2. Anyhow, you see that you must exclude the characteristics 2 and 3. And 3 is obvious because this is a square. The 16 singular points are obtained by a cyclical permutation of coordinates from the 4 points 0, 1, plus minus 1, plus minus 1. And this Y is nice. It admits a symmetry group, the semi-direct product of Z2 to the cubed, multiplying the coordinates by plus minus 1, times semi-direct product with S4. So it has many symmetries, and it is and the important thing is that the surface is defined over Z and also the singular points. Now, I want now to spell out an important fact, which is the relation between the co-theoretical notion of shortening and the geometric notion of smoothing and unobstructedness. So let me recall the well-known definition. A nodal hypersurface is said to be unobstructed if its singular points impose independent conditions on the space of polynomials of degree D. And unobstructedness implies that for each subset n prime of n, there is a small deformation y prime, which gives a smoothing of all the nodes which are not in n prime. And the key result, giving a relation between geometry and coding theory, is that if y prime is gotten from y smoothing the nodes in n minus n prime, then the code of y prime is the n prime shortening of the code of y. And so this is important because the cephaloquartic is unobstructed, and like all, in fact, nodal K3s. And so once I have a code, I get all its shortenings just by taking the smoothing. So the equations and the singular points of the cephaloquartic have integer coefficients. Since y is unobstructed, we get for each ni not greater than 16 real quartic surfaces with exactly new real nodes, and for each possible code K prime. And so the main point, why do we get, so what I have to show is that each extended code for a nodal quartic is a shortening of the Kummer code. And here I use the fact that these codes have only weights 8 or 16 for the vectors in K and 7, 11 for the other. And from this, I prove that they are all shortenings of the extended Kummer code. Let me say here that for the people who do coding theory, they do everything with the computer, and then they say, oh, obvious, and they produce a very long list, which for me is unreadable. So I had to do things by myself and really do some linear and bilinear algebra and prove directly these abstract results that these codes are just all the shortenings. So let's go back. The main theorem about quartics is that the subset of the nodal Severi variety corresponding to surfaces with fixed binary code K prime is smooth and connected. I explained how this follows from the Torelli theorem plus the reality condition and Nikulins results via the abstract classification of all possible codes. The possible codes are all the shortenings of the extended Kummer code. And carrying out this classification concretely shows that the components form 34 strata. And moreover, the condition that one stratum is incident to the other means that it is a partial smoothing, and so this happens if and only if the corresponding extended code admits the other as a shortening. So not only we describe the strata, but also the incidence relation. The picture, of course, is more complicated than the simple picture which I showed in the beginning, but is satisfactory. What is interesting is that the above methods allow also the description of Severi varieties of nodal K3 surfaces for all degree. The results are similar. Of course, all the codes depend on the residue class of D modulo 8, but for degrees higher than 10, there are some sporadic cases. It is not true that they are all obtained to smoothings of nodal maximizing K3 surfaces. Because in higher dimension, we can apply the theorem of Saint-Donat, and we can construct new nodal surfaces projecting from one node. The easy cases are D equal 2, because it's just studying sexting curves with nodes. And what is very interesting is the case of degree 6. It's the case of complete intersections of type 2, 3 in P4. And this is very important because the complete intersection of type 2, 3 in P4 are obtained from a nodal cubic hypersurface in P5, taking the Taylor development of the equation of X at one node. So this study was pioneered by a student of Van der Veer Kalker, but he didn't get any concrete result in a sense. And now let me come to an old story, which is the even sets of nodes. Classifying the possible codes relies on a crucial investigation, the determination of the possible weights. Here come into play geometry and homological algebra, and if we pass from code vectors, since we are binary code, is the same to speak of their support, and the set of nodes is said to be even or respectively half even if the sum of the sectional curves is divisible by 2 in the cohomology group of the resolution, respectively is this sum plus the hyperplexion is divisible by 2. And it was observed already in the 70s that the Riemann-Roch theorem implies that the cardinality of an even set of nodes is always divisible by 4 and divisible by 8 if D is even. So theoretical, as conjectured by Barth and myself, there is a theoretical answer. An even set of nodes, we just say delta even, so even or half even. Delta is just 0, 1. N is delta even if and only if there is a vector bundle on P3 and the symmetric map from E dual twisted by minus D minus delta to E, such that the surface is the set of points where the corank of this symmetric map drops by 1, and N, the set of nodes, is a set of points where the corank of this linear map is 2. We say that N is symmetric if E is the direct sum of line bundles, which means that alpha is a matrix of polynomials, and linearly symmetric if alpha is a matrix of linear forms. Unfortunately, this very nice theorem, which was inspired by some result of Walter, is a little bit theoretical because constructing these vector bundles is rather difficult. So let's go to quintics. If we have some new results, if we have an even set of nodes on a quintic, this cardinality, as I showed in 78, can only be 20 or 16. And for 20, it corresponds to a matrix 5 by 5 or linear forms. And 16, if you get a 3 by 3 matrix with diagonal entries of degrees 1, 1, 3. Recently, I showed together with Sandro Verra that if a nodal quintic has an even set of cardinality 20, then its number of nodes is at most 28. And the case where nu equal 28 via prim theory leads to an irreducible component of the nodal severity variety of quintics with 28 nodes. So this leads to a simpler proof of Beauville's theorem that the nodal quintic has at most 31 nodes. And the main point is that if there are even sets of cardinality 20 or 16, but if you have an even set of nodes of cardinality 20, the number of nodes is 28. So it assumed that it has at least 29 nodes, then an even set of nodes has cardinality 6. But I showed in the beginning that if the weight of a code is a power of 2, then we have an inequality that it is a subcode of the biduality code. Therefore, k is at most 5. Now, the very nice observation by Beauville is that the dimension k, however, is at least ni minus 26, because Beauville observed that the dimension of isotropic subspace is at most half of the dimension of a space. And so I called now in the paper this the Beauville inequality. So from the Beauville inequality, k is at least ni minus 26, and this other inequality, it follows that ni is at most 26 plus k is at most 5, and we have that ni is at most 31, equality holding if and only if we have the biduality code. Now, let's go to the Togliatti quintics. The existence of quintics with 31 nodes was shown by Togliatti, the elder brother of Palmiro Togliatto, who was the leader of the Communist Party in 1940, even if he didn't verify all the details. And he constructed as discriminants of the projection of a cubic hypersurface in P5 with 15 nodes from a general line contained in this cubic hypersurface. And this is the method of cubic discriminants, which I shall explain in the end. Barth gave an explicit equation of a quintic with 31 nodes using symmetries. And recently, my collaborators Kaufman and Frapporti gave an explicit equation of a Togliatti quintic using the method of Togliatti. And this is the nice, as I get a matrix 3 by 3, the entries here are linear forms. This is a cubic, these are quadrics. And this has exactly 31 nodes and no other singularities. Here, this cubic is the Cayley cubic. And anyhow, this is an explicit equation obtained projecting, taking the projection of a cubic hypersurface in P5 and projecting from a line contained in it. So this is an explicit equation of Togliatti type. Now, for quintics, the situation is as follows. We can prove that the spaces, the Severi varieties of Togliatti quintics and Togliatti cubics are irreducible. And I have to say that these results depends heavily on the study of nodal varieties of K3 surfaces of degree 6. And for ni at least 29 nodes, there is a correspondence between the reducible components of the variety of quintics with ni nodes and cubic hypersurfaces with ni minus 16 nodes. And these are classified. If you take 28 nodes, there is exactly one component for which K contains 2 code words of weight 2. And all the codes of Nodal quintic surfaces are just shortenings of the simplex code, or the shortenings of the unique two-dimensional code with two code words of weight 20. This corresponds for the prim case found together with Verra, and there is only one gap. Can we have the unique two-dimensional code with exactly two code words of weight 16 and one of weight 10? So the classification is not yet complete. There is a case missing. Let's go to the sextics, which is the most interesting and mysterious. So sextic, the Barth sextic has an explicit equation where tau is the inverse of the golden ratio. And Barth used the study of the invariants done by Felix Klein for the action of the icosahedral group, A5. You see immediately that there are 6 planes intersecting y in a cubic counted with multiplicity 2. For instance, here you take tau squared, if you take tau x minus y equals 0. So here you have 2 linear forms, 2 linear forms, 2 linear forms. And if any of these 6 linear forms vanishes, then we get a square. So if we intersect with each of these 6 plates the Barth sextic, we get the square of some equation W times a conic. And in this case, we see that on this plane, there are 15 nodes where the this quintic vanishes, this cube vanishes, and these 15 nodes form a half-even set. So what is important is that from the symmetry of the equations, you can construct a lot of code words. For instance, half-even sets with cardinality 15. And now we have 5 more such half-even sets of cardinality 15, and they are orbit under the icosahedral group A5. And Yonghwa Cho, my collaborator, proved that essentially the extended code, to be more precise, the projection of the extended codes is generated by the half-even sets of cardinality 15. And so he was able to effectively describe the codes for the Barth sextic. Now, this description was complicated, but it turned out that it's possible to describe these codes in a more conceptual way. So it seems that the codes of the Barth sextic are related to a graph found by Doro and Hall many years ago. The code of the Barth sextic is isomorphic to the code generated by the characteristic functions of maximal independent sets of the Doro-Hall graph. So a maximal independent sets means a maximal set M such that no edge joins two vertices. This graph is a regular graph with 65 vertices, which is locally Petersen. The Petersen graph is the dodecahedral graph divided by antipodal involution, and has the property that each vertex has 10 vertices at distance 1, 30 others at distance 2, and 24 at distance 3. And the smaller code K is generated by the characteristic functions of the 65 spheres of radius 3 in this Doro-Hall graph. And so there is some interesting connection. And what is the way that Doro constructed this graph, Doro constructed the graph via group theory. You take the group of collineation on the projective lines over a field with 25 elements, which is a semi-direct product of PSL to F25 times Z-mod2, where Z-mod2 is generated by Frobenius. The non-normal subgroup is the one generated by the Frobenius, and Frobenius is a semi-projectivity. Recall that F25 is obtained from the field with 5 elements adjoining the square root of 2, and Frobenius sends the square root of 2 to minus square root of 2. And Doro constructed the set of vertices as the conjugacy class of the Frobenius automorphism, with an edge connecting two elements if and only if these two elements commute. And Hall later showed that this was the large class of the so-called locally Peterson graphs. And here I repeat, the Peterson graph is the graph associated to the vertices of the projective dodecahedron, the quotient of the dodecahedron by the antipodal map. Now, what is interesting is that there exists a projective geometry description of this graph. Now you take the Barth sextic and you associate to it a graph whose vertices are the nodes of the sextic, B stands for Barth, and where an edge joins two vertices if and only if the line joining the two vertices intersects the sextic in two more points with multiplicity 1. So the general behavior of a line connecting two nodes is the one which tells there is an edge in this graph. And then this graph is isometric to the Doro-Hall graph. Now, what is somehow interesting is that the Peterson graph is associated to the dodecahedron, and the dodecahedron is dual to the icosahedron. And the Barth surface is constructed from the icosahedral symmetry. So is it possible to find a direct explanation of the relation why this geometric graph corresponding to the nodes of the Barth surface is the Doro-Hall code? This is a tantalizing question, but I could not find yet an answer. Now, let's go to sextic surfaces with 65 nodes, other. And so there was a lot of work with Casnati and Tonoli, Jeffrey and Ruckberman, and we know that the cardinalities of an even set of nodes on a sextic are exactly the elements of the set 24, 32, 40, 56. And with this information, and with about 1 year of computer time, Sasha Kurz in Bayreuth was able to prove that the extended code of a nodal sextic with 65 nodes is isomorphic to the one of the Barth sextic. So this is really a brute force theorem, and but it is somehow what we were hoping to show. 65 nodes, then the code is the one of the Barth sextics. And here, the situation, unfortunately, we could not find but a partial classification of the half-even sets on sextics. And even their cardinalities are not determined. 15 occurs, 19, 23 do not occur, 27, 35, 31, 35 39, 43, but we don't know whether 47. But there is a case, we can say that a half-even set of nodes with cardinality 31, which is the sum of a half-even set of cardinality 15 with an even set of cardinality 4, is symmetric. So it corresponds to the description of the surface as the determinant of a matrix of forms with diagonal entries of degree 1, 1, 1, 3. And here, Yongba Cho found an explicit description of the Barth sextic as a determinant of a matrix. Here is a 3 by 3 matrix of linear forms. These are quadratic forms. And here is a cubic form. And now this is related to the description via cubic discriminants. So this is the last thing which I want to talk. So if I have a cubic hypersurface in Pn and L a linear subspace of dimension k, and then there is some inequality that if L is contained in the smooth locus of X, we have that 2k is at most n minus 1, and 2k is at most n if X has isolated singularities along L. So I will skip this proof. What is important is that we can take coordinates, this coordinates z and x, and L is the subspace where the x coordinates equal 0. And then, since L is contained in the cubic, we can write the equation according to the Taylor development in the x. So I have some aij of x times zi zj plus quadratic forms in x times zi plus a cubic. And in this way, if we project with center L to the space with coordinates x0, x1, xp, so I take a linear subspace and I project to PB. This rational map extends to a morphism of the blow-up with center L, and the fiber is the join of L with the point X and intersects X in a linear subspace plus a quadric. And this quadric has this matrix. So if I take this development, this aij gives me some matrix of linear forms. This quadrix gives me the first part of this column and the first part of this row. And so you see that to y, so the discriminant of this projection is the points x such that this matrix has trivial determinant, which means that this quadric has singular points. So we take the projection to P3, we take discriminants surface of degree 4 plus k, and now Togliatti quintics occur as discriminants of a Togliatti cubic hypersurface, one with the maximal number of nodes, 15, and the 35 nodes are an even sets of 16 nodes plus 15 nodes projection of the 15 nodes of X. Now we have a similar result for sextic with 65 nodes. And the next theorem says the Barth sextic is a smooth point of an irreducible component of dimension 18 of the variety of sextic with 65 nodes. And every nodal sextic with 65 nodes is the discriminant of a cubic hypersurface with 31 nodes for the projection with center a plane passing through 3 nodes. The 65 nodes consist of a half-even set of nodes of 31 nodes, 28 nodes projection of the nodes in X minus L, plus 2 nodes for each node in L. So we get a uniform description of this 65 nodal sextic as discriminants of this cubic hypersurface with 31 nodes, projection from a plane passing through the three nodes. Now, the maximal number of nodes a cubic hypersurface can have is determined, and in even dimension, this is obtained by the Segre cubic, S1 equal S3 equals 0. And I will skip this. And what is interesting is that we cannot take the discriminant of the Segre cubic in P6, which has the maximum number 35 of nodes. And this happens because all the planes contained in X are contained in a linear subspace of dimension 3 contained in X. And moreover, it's quite difficult to see, but we cannot take a cubic with 34 nodes. And each sextic with 65 nodes can be a discriminant of a cubic hypersurface only if the plane passes through one node. So there are several possibilities, and the situation is not completely clear always. And let me just take 1 minute more to mention an interesting open question. Stephen Kaplan and Davide Frapporti show the following. If you take the Segre cubic, the one with the maximal number of nodes, any equisingular deformation of the Segre cubic is projectively equivalent to the Segre cubic. And the same for the Goryunov cubic if the dimension of the projective space is at least 7. And the Segre cubic is unobstructed. So Segre indeed showed considered the nodal maximizing cubic in P4 and proved that there is only one case. And now there is a natural question. Is it true that every nodal maximizing cubic hypersurface in PM is projectively equivalent to the Segre cubic when n is even, and for odd dimension of the projective space, at least 7 to the Goryunov cubic? Well, now the unobstructed of the Segre cubic gives another proof that there exists an irreducible family of cubic hypersurfaces with 31 nodes, depending on 3 moduli, and so an irreducible family of dimension 18 of sextic with 65 nodes. And it's an open question whether the method of cubic discriminants help understand the nodal maximizing surfaces of degree 7 and 8. And I stop here. Sorry for going a couple of minutes over time.
Thank you, Fabrizio. Let's thank Fabrizio for a beautiful talk. And it was very nice. Fabrizio, let me first ask questions myself, and then I ask people to ask questions. So regarding, I have 2 related questions. So one of them that regarding your determinantal expression for this Barth sextic.
Yes.
So, you know, Barth sextic can be obtained as a ramification surface if you project some determinantal quartic with many nodes. I think with 43 nodes, if you...
Yeah. This was...
Peterson, student.
Peterson, yeah.
Yeah. So is there a relation between this determinantal quartic and your determinantal equation? Well, maybe no. We'll just...
I'm not sure. I mean, I didn't. That's an interesting question. I mean, I know that, yeah, there is this family,
Yeah, there's a, I think, three-dimensional something of determinantal.
Yeah, it's just exactly, no. You see, the main problem is how to prove that a family of, I mean, you see, we have families of sextic with 6-5 nodes as dimension 18, but it has 3 moduli, okay? Because 15 are the projectivities.
So I think all of them
for the Barth, it is possible to prove that it is unobstructed.
Mhm.
This shows that this family has local dimension 3,
Mhm.
so 3 moduli. The same thing, now I don't know exactly whether this Peterson, he constructed a 3-dimensional family.
It should be the same.
It should be the same, yeah. Then there is another family, because I take the Segre cubic, which has 35 nodes. And now this is unobstructed, okay? And so I know that I can deform, I can smooth independently. I can smooth independently exactly 4 of the nodes.
It's okay, Fabrizio. Don't need to answer now. It just was question, just came to my mind.
No, I'm getting a little bit confused now because, yeah, of course. I mean, 35. So now, in fact, I'm getting confused that the dimension, the Segre cubic has 35. So this should give, maybe I made a mistake here, that is 4 moduli.
I have another question, which actually relate to the quartic case.
No, this is interesting. Okay, but yes, please.
Yeah. Can you scroll back to your main theorem about quartic?
Yes.
Somewhere in the beginning. Yeah. In this case, you get a complete answer.
Yes.
Which is very nice. Yeah. I think it's here. No.
I know, maybe the first.
The very beginning. Yes.
Okay, so yes, this is the theorem of quintics.
No. I mean for irreducible number of components. So how many?
Here.
This one, yeah. Okay.
The Nodal Severi. So this is.
Yeah. So my question is like this: when I look, I usually think about quite often about quartic surfaces as in terms of the double cover. So you have this quartic double solid and the corresponding birational geometry. So is it true that each irreducible component basically correspond to quartic double solids with a fixed, I must say, class group?
With a fixed
class group. So, for example, if you take six number of six points, 6 singular points. If you take a double cover, you have 2 types of quartic double solids with 6 nodes. For one of them, the class group is Z, and another one, class group is Z plus Z, which obtained from the cubic threefold projecting from a point.
Yeah, this is a very interesting.
This is exactly your 2 models.
Vanya, I think that essentially the answer to your question should be easily gotten, you see, from the description of the code, because you know exactly what are. I don't. I have some other paper here. The paper is the long paper is there. So there is an explicit. There is in one for nu equals 6. In one case, the code is trivial, and in one case, the code is non-trivial.
Yeah, it's exactly correspond to the class goal.
And because nu equals 6 means that the quartic surface is a determinant of a matrix which has linear form cubic. So it's a linear form times cubic minus square of quadric. And this is exactly the relation you're looking for.
Exactly. So my question is, probably in the other cases, it's going to be the same. You can see birational geometry of this quartic double solids.
I think that this should really shed light on the geometry, complete light on the. I should point out here that see, what is important here was the description of these codes K prime as a shortening. You can, I mean, some people, I mean, you can really classify these codes, but in order to prove that they correspond to components, you must say that they are shortenings. For instance, there is Endras, he pointed out that in the book of Ron, about quartic surfaces with nodes, the classification is not complete. So in a sense, this is it should gives a complete and clean classification. And in fact, I can describe explicitly. I mean, once I have this Reed-Muller code, and then I just take all the possible shortenings, and so it's elementary linear algebra on subspaces on fine space.
Okay, thank you, Fabrizio. Sorry, I took too many questions. So let me ask people for questions. Please, if you have a question to Fabrizio, please ask. Any questions to Fabrizio? Okay, if no questions, let's thank Fabrizio one more time for beautiful talk.
Okay, thank you.
Yeah. Thank you. Okay, thank you very much, and thank you, Fabrizio, and stay safe, and see everyone next week.
Okay, yeah. Thank you. Bye-bye.
Bye.
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 Bye, Fabrizio. Bye-bye.
Ciao, Federico.
Bye.